I welcome you all to the session of applied thermodynamics, and today we shall discuss about the velocity diagrams, work transfer, and then finally discuss about the efficiency of a reaction steam turbine. So, if you try to recall, in the last class we have discussed about reaction turbine and we have tried to discuss the difference between the reaction turbine and impulse turbine, you know, and we have also introduced one term, that is degree of reaction. So, in fact, we have understood what do we mean by degree of reaction, and from there we have seen that from the enthalpy drop in the moving blades, rather the relative magnitude of the enthalpy drop in the moving blades rather leads to the classification of different types of reaction turbine. Okay. So, now you know that we had defined this degree of reaction equal to delta H moving blades by delta H total, right. So, in a way, as I have discussed that this quantity signifies the relative, rather the fraction of the enthalpy drop in the moving blades. So, you know that this H delta H total, this is nothing but delta H fixed blades plus delta H moving blades. So, the fixed blades, that is nothing but nozzle. So, now basically when delta H moving blades equal to delta H fixed blades, in that case R equal to what? Equal to delta H stage by 2 equal to half. So, that is 50% reaction turbine. Okay. Now, today we shall try to understand that for what will be the velocity triangle at the inlet and velocity triangle at the outlet for the 50% reaction turbine. Now, if we try to draw, we will be getting, before that let us briefly draw the blading. So, it will be, so as we have discussed that okay, and so steam is coming, so this is moving blades and this is fixed blades, and these two constitutes together to form a stage. So, this is one stage. Okay. Now, you can see that we have discussed that this is the row of, this is first row of moving blades, and if we try to compare the, in fact, in case of impulse turbine initially we had nozzle where entire pressure drop takes place, but in case of the reaction turbine the nozzle in pressure drop takes place both in the fixed blades and as well as in the moving blades. So, this is fixed blades or nozzle. So, this is or nozzle. Okay. So, if we try to draw the velocity and pressure distribution, say I will be drawing using red color. So, this is pressure, you know, pressure falls, then again slight pressure drop. So, this is P naught, this is P 1 and this is P 2. Okay. And if we try to draw the, so this is, so basically this is P naught C naught. Okay. So, this is P 2 C 2 and this is P 1 C 1. So, that is at the inlet of the moving blades or exit of the fixed blades. Now, question is, if we try to draw the velocity distribution using different color, say this is C naught and then this is C 1 and then we will be having pressure drop. So, this is C 2. So, try to understand that there is a pressure drop both in the fixed blades as well as in the moving blades, right. Also velocity increases while steam is passing through the fixed blades, and that is what is needed, because steam eventually will strike the blades or moving blades in the form of a jet. Also there is a change in pressure drop, as a result of which there will be slight increase in the kinetic energy. So, that is what is very important to understand. When steam is passing through the passage between two consecutive blades in the moving blade row, then pressure falls, that is seen from this pressure distribution. So, P 2 is less than P 1, right. So, P 2 is less than P 1. So, accounting for this pressure drop, there will be an increase in the kinetic energy of steam as it passes through the row of moving blades, and that is why we have discussed that the shape of the moving blades are in the nozzle shape. Since it is of the nozzle shape, I mean blades are of the nozzle shape. So, there will be slight increase in the kinetic energy of the steam even when the steam is passing through the moving blades. So, now let us draw the velocity triangles and then it will be clear. So, I am writing R equal to, again I am writing delta H moving blades by delta H fixed blades by delta H moving blades. So, this is delta H total. Okay. Now, so mind it, velocity triangles for R equal to half, right. So, 50% reaction turbine. Okay. So, let us draw the velocity triangles. So, this is V b, that is blade velocity, and if we say so, this is the inlet velocity diagram. So, this is the inlet velocity diagram. Okay. Now, so this angle is alpha 1 and this angle is beta 1. That is what we have seen in the last class. I mean velocity triangles which we have drawn in the context of the impulse turbine. Okay. So, now this is Okay, so, this is beta 1. Now, this is inlet velocity triangle, say this is A, B, C. What about the outlet velocity triangles? So, this is, mind it, this is 50% reaction turbine. This angle is alpha 2 and this angle is beta 2. And say this is D, right. So, this is D. Here I have to give, right. So, this is which is important. Now, right. So, this is what is very much needed. Okay. So, question is, if I try to draw using red color, this angle is delta. Okay. See, if you try to recall, I mean for the impulse turbine, the relative velocity was less, say this is B B prime. So, this is B B prime. For the impulse turbine, the relative velocity was B B prime and this was the absolute velocity like this, right. But now you can see the relative velocity is higher, that is from B prime to D. This small I mean, so velocity this amount is there for the reaction turbine. Can you tell me why it is so? See, in case of a reaction turbine, if we try to go back to the previous slide, here as I told you that impulse action is there, right. Impulse action is there because of this change in momentum, as the jet is having a change in the change in its direction. So, when steam in the form of jet is striking the blades, rather moving blades, it is getting deflected as it passes through the row of moving blades, and because of this change in direction, momentum change will be there. So, impulsive or because of this impingement action, I mean we will be getting this impulsive effect. Okay. So, impulse effect is there. On the top of that, what I told that that as the steam is passing through the row of moving blades, there is a little change in kinetic or gain in kinetic energy. So, when the steam is coming out from the moving blades, right. So, a reaction force is impressed by the jets on the blades in the opposite direction, right. So, because of the relative increment in the kinetic energy as the steam passes through the row of moving blades, a reaction force, so kinetic energy is getting increased. So, a reaction force will be there, and because of this, as I told you that C 2 is even greater than C naught, C 2 is greater than C naught. So, still because of this high absolute velocity, so relative velocity also will be higher because blade velocity is same, try to understand. So, C 2 is greater than C naught. So, because of the shape of the moving blades, which are the shape is of the nozzle shape, the relative increment in kinetic energy, because of this a reaction force will be impressed by the leaving jet, and that will be impressed by the jet on the blades, and that is in the opposite direction, Newton's second law. So, we are having impulsive effect. On the top of that, we are also having a reaction force that is being developed by the leaving jet on the blade, as a result of which that it is called, I mean both effects will be there while turbine is rotating. So, impulse reaction turbine, that is why the name is there, but as I told you, only to differentiate this class of turbine from the impulse turbine, this turbine is called simply reaction turbine. So, that is what I have discussed in the last class, but now only to discuss that why. So, you can understand the absolute velocity leaving the first row of moving blades will be even higher than the absolute velocity which is entering into the moving first row of fixed blades, and since the absolute velocity is still higher and blade velocity is fixed, so the resultant effect relative velocity will be higher, right. That is why this relative component, so this amount is higher, this amount is higher only because of that. So, now because of this relative velocity, so reaction force is there, so you can see these two velocity triangles are similar. So, I can understand, so delta ABC and triangle BCD are similar. Okay. Try to understand, we are having 50% reaction turbine. If it is 50% reaction turbine, we can write delta H MB equal to delta H fixed blades. Okay. If that is the case, right, if that is the case, C1, so I am giving name now. So, it is better to give the name. So, this is W1, this is C1, this is W2 and this is C2, right. Now, since delta H MB is equal to delta H FB, C1 equal to W, C1 equal to W2, right. Relative velocity will be higher. So, that is what I have been discussing. So, because of this higher C2, this amount of relative velocity should be higher, and since the degree of reaction is enthalpy drop in the moving blade is equal to enthalpy drop in the fixed blade. So, C1 equal to W2 and also beta 1 equal to beta 2 equal to alpha 1, beta 2 equal to alpha 1. Now, if these two triangles are similar, we can write. So, this is basically coming from the fact that, let me write it, fixed blades and moving blades are made similar in shape. Okay. So, we can write, this is what we need to ensure. As I told you that moving blades and fixed blades are geometrically similar, similar in shape. Okay. So, beta 2 equal to alpha 1, since these two triangles are similar. So, from this we can write, again I am writing triangle ABC and triangle BDC are similar. So, C2 equal to W1 and beta 1 equal to 180 minus delta, right. So, beta 1, so this angle will be equal to this angle. So, try to understand from the this velocity diagrams. So, this beta 1 will be equal to alpha 2, that is nothing but 180 minus delta. Okay. So, that is what I have written. Now, question is, this beta 1 is not equal to beta 2 as blades are not symmetrical. Okay. Since blades are not symmetrical, blade angles are not equal. Blade angle at inlet is beta 1 and blade angle at outlet is beta 2, right. So, now what we can write, and try to understand from this figure. See, had the velocity relative velocity been like velocity relative velocity that we have seen in case of an impulse turbine, we would not have this extra component, right. But here we are having this additional amount, additional magnitude of this velocity, as a result of which you can see the delta V A, or rather delta C A I will be writing, delta C A equal to 0. So, there is no any axial thrust to be precise. So, delta C A equal to 0. So, it implies no axial thrust. We have seen in the context of impulse turbine that because of the difference in the magnitude of the relative velocity components, we had axial thrust, but here we really do not have axial thrust, because relative velocity at the exit of the moving blade is equal to the relative velocity at the inlet of the moving blade. So, there is no axial thrust, but there will be axial thrust that we really cannot ignore, as why this axial thrust will be there. So, when steam is passing through the row of moving blades, pressure will slightly change, and that you can see from this diagram. So, because of this reduction in pressure drop, slight axial thrust will be there. So, though theoretically there is, we can say that no axial thrust will be there as delta C A equal to 0, but in actual or in real practice, as the steam passes, when the steam passes through the row of moving blades, there is a reduction in pressure that we have seen, and because of that we will be having slight thrust. Okay. Now, we need to understand what is work transfer, right. So, work transfer W equal to, or let us say I am write W d, or sometimes it is known as diagram work, equal to delta C theta into V b. So, this delta C theta is nothing but the change in swirl velocity. Okay. So, we have to calculate what is delta C theta. See, delta C theta, this delta C theta equal to nothing but C theta 1 minus C theta 2. I am taking only the magnitude. Okay. So, you understand what is C theta 1? C theta 1 is nothing but the component of absolute velocity in the tangential direction. So, that is C 1 cos alpha 1. Okay. So, I am writing here C theta 1, that is component of absolute velocity in the tangential direction, right. So, let me tell you, this is the tangential direction, this is the axial direction. Okay. So, now that is nothing but C 1 cos alpha 1. Similarly, C theta 2 will be equal to C 2 cos delta, right. So, let me so this is C 2 alpha 2 nothing but 180 minus what I can say, let me write it, it is in a, I will write it cos alpha 2. So, this is alpha 2 equal to C 2 cos 180 minus delta, right, 180 minus delta. Okay. So, if we plug in the value of then delta c theta, which is nothing but c theta 1 minus c theta 2 will be equal to c 1 cos alpha 1 minus c 2 cos delta. Okay. So, that you can write c 2 cos delta. Okay. So, now question is what is c 2 cos delta? So, if we go to that next slide. So, delta c theta equal to c 1 cos alpha 1 minus c 2 cos delta. Okay. So, c 2 cos delta can we write that is nothing but W 2 cos beta 2 minus V b. Try to understand. So, this this is c theta 2, right. Now, total is W theta 2. So, W theta 2 minus V b is equal to c theta 2. So, W theta 2 is, so I can write here W theta 2 minus V b equal to c theta 2. Therefore, W 2 cos beta 2 minus V b equal to c theta 2, that you can write, very simple. So, this is known as W theta 2 total, this total is W theta 2. Okay. So, now W theta 2, in fact I can write over here, that will help you. So, I can write that this is c theta 2 and this is W theta 2, right. So, now if we plug in the value over there, then we can write that c 1 cos alpha 1 minus c 2 cos delta 2 is equal to, you know, it would be W 2 cos beta 2 minus V b. So, if I take the mod value of this, so it will be plus, this will be minus. Okay. So, you know that from the, you know, we know that C 1 is equal to W 2 and beta 2 is equal to alpha 1, right. So, we can write this equal to C 1 and we can write alpha 1. So, it will be coming 2 C 1 cos alpha 1 minus V b. See, you also can write this delta c theta equal to from the velocity triangles, right. You can simply write from this velocity triangle. See, it is nothing but W 1. So, basically you have to find out c theta, so that is total. So, W 1 cos beta 1 plus W 2 cos beta 2. So, try to understand, let me draw the velocity triangles again. So, see, you have very quickly, I have to complete it now. So, okay. So, this is W 2, this is C 2, this is C 1, this is W 1. So, now this is C theta 2. So, that is C theta 1, this is C theta 2. Okay. So, what is this? This is nothing but this is W theta 1 and this is W theta 2. So, you know this angle is beta 2 and this angle is beta 1. So, you can write this is nothing but W theta 1 plus W theta 2, right. From the geometry you can write. Now, W theta 1 is equal to W 1 cos beta 1 plus W 2 cos beta 2. Just I can derive the same expression from different angles. So, that is cos beta 2, right. Now question is, what is W 1? W 1 equal to, that is what I have written, W 1 equal to C 2 and beta 1 is equal to 180 minus delta. Okay. So, if I write here W 2 equal to C 1 and beta 2 equal to alpha 1, right. So, beta 2 equal to alpha 1, that you can understand, alpha 1 equal to beta 2 equal to alpha 1 and W 2 equal to C 1. So, we are trying to write this expression. So, you know that from here we can write what is W 1 cos beta 1. So, W 1 cos beta 1 is nothing but C 1 cos alpha 1, sorry, C 1 cos alpha 1, C 1 cos alpha 1. So, this angle is alpha 1. So, this angle is alpha 1. So, this C 1 cos alpha 1 minus V b. So, C 1 cos alpha 1 minus V b, that is nothing but W theta 1. So, C 1 cos alpha 1 minus V b minus plus W 2 cos beta 2. So, that is C 1 and beta 2 is equal to alpha 1. So, C 1 cos alpha 1. So, it is coming 2 C 1 cos alpha 1 minus V b. So, this is the expression of delta C theta. So, now if we quickly write work transfer or diagram work equal to delta C theta into V b, that is twice C 1 cos alpha 1 minus V b into V b. Okay. So, this is, now we need to find out efficiency. Next is efficiency, diagram efficiency. So, I am writing diagram efficiency or blading efficiency. That is eta d. So, that is nothing but what? Energy. So, you know that work produced by energy input, right. So, if we try to write it, that is nothing but 2 into 2 C 1 cos alpha 1 minus V b into V b divided by energy input to the blades in the form of a steam jet. So, work done by this steam on the blade to the energy input to the blade in the form of a jet, right. So, this is basically work done by the steam on the blades to the energy input to the blades, that is in the form of a jet. So, now what is energy input? This is very important, you have to try to understand. So, energy input per kg of steam, if I am per kg of steam flow, if I try to write it per kg of steam flow or per unit mass flow, rather per unit mass flow of steam Okay. So, that is nothing but you have seen C1 square by 2 plus it would have been half m C1 square ms because that is per unit mass of steam. So, basically half C1 square plus see for the impulse turbine we have seen this is only the energy input, but no, in case of a reaction turbine, you know, in case of a reaction turbine, if we go back to the previous slide wherein I have drawn the blades, see impulse action is there, on the top of that we are also having the reaction force, and that reaction force is developed only because of the reduction in the relative velocity. So, basically when the steam is passing through the row of moving blades, there is a change in kinetic energy and that change at the cost of the pressure drop. So, basically that leads to a reaction to the blades in the opposite direction. So, basically that will be, that term will be there. So, that is nothing but half into W2 square minus W1 square, right. So, you know that if we look at the velocity triangles, here this additional amount of the relative velocity that was not there when we have I mean for the impulse turbine that we have seen from the velocity triangles, but here we are having. Why this increment in relative velocity is there? Because C2 will increase, and as Vb is remaining same, for increase in C2 the resultant also will increase the relative velocity, right. So, as we have discussed, again I am telling, because the shape of the moving blades are the nozzle shape, as a result of which when steam is passing through the row of moving blades, kinetic energy will increase. Now, if we try to draw the velocity triangles, so C2 will increase compared to the C naught, and as a result of which Vb is remaining fixed, C2 will increase, the resultant, that is relative velocity, will increase, right. So, the W2 will increase. Now, since W2 is increasing and W2 will be higher than W1, W2 will be higher than W1, and as a result of which you will be getting reaction force. So, when we are trying to obtain the input energy, so we need to consider the change in relative velocity as well. So, this is change in due to the change in relative velocity. Okay. So, now if we simply write, so this is C1 square by 2, since W2 is equal to C1, so C1 square by 2 minus W1 is equal to, so W1 square by 2, as W2 equal to C1 that we have already written. So, it will be C1 square minus W1 square by 2. So, this is the expression. Now, what is W1 square? I mean, if we try to draw, this is the inlet velocity triangle. So, this is C1, this is W1. And this is Vb, and this angle is alpha 1, this angle is beta 1. So, can't we write W1 square equal to C1 square plus Vb square minus 2 C1 Vb cos alpha 1. Just the formula of cosine angle we have used. So, if we plug in the value over here, we will be getting, that is C1 square minus Vb square, right, plus twice C1 Vb cos alpha 1 divided by 2. So, divided by 2. So, this is the expression of the input energy. So, if we try to plug in the value of there, then we will be getting efficiency. So, eta d will be getting, I am writing 2. So, basically 2 into 2 C1 cos alpha 1 minus Vb into Vb divided by C1 square minus Vb square plus twice C1 Vb cos alpha 1. Okay. So, we can write this in this form, twice Vb square into twice C1 cos alpha 1 by Vb minus 1 divided by C1 square into 1 minus Vb square by C1 square plus twice Vb by C1 cos alpha 1. Okay, so, I can write in this form. You can understand we are trying to write in the form of, so we are defining velocity ratio. Velocity ratio, that is what we have done even in case of the impulse turbine. Vr, that is nothing but Vb by C1. So, if we write this, then we can write eta d equal to we can write 2 into twice cos alpha 1 by Vr minus 1 into Vr squared divided by 1 minus Vr square plus twice Vr cos alpha 1, right. So, now if we try to find out optimum speed ratio or velocity ratio for which eta d is eta d maximum, right. So, what we need to do? We need to do d eta d by d Vr equal to 0 and we will be getting Vr optimum will be equal to C1 cos alpha 1. So, this is very important, I am underlining, and eta d maximum will be equal to twice cos square alpha 1 divided by 1 plus cos square alpha 1. So, this is the objective. So, I did not do this task because this is very simple. Objective is by defining velocity ratio, we can try to find out optimum velocity ratio for which the diagram efficiency or blading efficiency will be maximum, and that is shown by here, and for that V optimum we can find out the maximum value efficiency. Okay. So, this is very important. Now, question is what will be WD maximum? That will be, again we know that WD maximum will be just if you plug in. So, twice, sorry, it should be twice into Vb minus Vb into Vb, that is Vb square, right. So, basically you understand that twice C1 cos alpha 1 minus Vb into Vb. Okay. So, this C1 cos alpha 1, that is, right. So, C1 cos alpha 1 is Vb optimum. Okay. So, this is Vb optimum. So, we will be getting Vb optimum square. Okay. So, now you try to understand. So, this is the blading work or diagram work corresponding to maximum blading efficiency. Okay. Now, if we try to draw the velocity triangles for this 50% reaction turbine, with maximum blade efficiency, So, 50% reaction turbine with maximum eta d, then it will be like this. It will be like this. So, then we will be getting Okay. So, this is W1, this is C1, this is W2, this is C2. Okay. So, this is beta 2, this is beta 1, this is alpha 1 and this is alpha 2. Alpha 2, alpha 2. So, this is basically let me erase it. So, this should be in this direction, right. So, see, try to understand the this is the velocity triangles, that is velocity triangle at the inlet. So, this is A, this is B, this is C and D, that is for the 50% reaction turbine with maximum blending efficiency. To summarize today's discussion, so we have discussed about the the velocity triangles for the 50% reaction turbine. We have discussed why the extra relative velocity component is there. From there we have tried to quantify the work transfer or diagram work, and finally we have tried to we have established the efficiency, and again from the efficiency by quantifying the velocity ratio we have expressed the optimum velocity ratio, and finally for the optimum velocity ratio we have calculated maximum efficiency as well as the maximum work transfer. So, with this I stop here today and we shall continue our discussion in the next class. Thank you.